Hi everyone. Today we are jumping into Unit 7, and the focus on Unit 7, which is a pretty short unit, is differential equations. Now, that sounds intimidating. I will tell you that differential equations are actually a very, very large mathematical topic. Like in college, they offer entire classes just called differential equations. Um, and you already know what a differential equation is. A differential equation is essentially an equation that involves a derivative, but there's all sorts of things you can do with these in equation form. And we're just going to see like the tiniest tip of the iceberg here in this unit. So we're just getting to know a couple of things that we can do with these differential equations. The first thing we're going to talk about, and that's what this video is focused on, is slope fields. So slope fields are a way to look at a picture of a differential equation that will help us visualize the solution. It's a visual tool for us. And I kind of skipped over a couple of things here. I skipped over initial condition. I skipped over what the idea of a solution really is. That's because I think it'll make more sense if we just talk about it with the examples. So if you do need to pause the video to get that vocabulary down, feel free to do that. But I'm going to hop right into what is a slope field? What does it do for us? So, like I said, a slope field is a way to visualize what's happening with a derivative. This is a derivative equation, so technically this is a differential equation. You've already been working with things like this, right? Where I say here's a derivative, here's its expression. What we're going to do is we're going to consider like the XY coordinates at all of these spots. So this is just a regular coordinate plane. It just happens to have dots drawn in. And we're going to draw line segments that represent tangent lines. So this differential equation is a pretty boring one because it only involves x, which means that all I care about really is the x coordinate at all of these spots. So for example, right here, x is equal to 0. So when I plug a 0 in here, I get a 0 back out, which means I have a slope of 0, right? And this is what a slope of 0 looks like. It's just a little horizontal line. And anywhere x is 0, I'm going to get a slope of 0. So this would be 0, this would be 0, this would be 0, this would be 0. Okay. When I plug a 1 in, so right here, x is equal to 1. 3 times 1 squared is 3. And so what you'll notice I'm going to try to do is draw a little line segment that would have a slope of 3. Now, no one is coming in here and busting out a ruler and trying to tell whether or not that actually is like a rise over run 3 over 1 kind of thing. The whole idea is to be relative about it. So a 3 should be higher than a 2, and a 2 should be higher than a 1. And so like in this next set, this is where x is equal to 2. If I put a 2 in here, 2 squared is 4, so this gives you a slope of 12. That should be like way steeper than the 3. Okay, almost vertical. We don't want to make it all the way vertical, but almost vertical. Okay. So let's go over here. This is where x is equal to -1. But since I'm squaring it, -1 squared is still 1. And so this is also all going to have a slope of 3. I'm a little high on that one, but these are all slopes of 3. And then over here at -2, again, -2 squared is 4. So these are going to be 12s as well. So if you kind of take a step back here, you should sort of see like a path through the maze, right? You should sort of see what this original function may have looked like. So I'll just kind of trace out, and this doesn't have to be perfect, but this graph may have looked something like, oh, let's see, like that. Okay, probably should have come up a little higher there to try to hit some of those tangent lines. But that's what we think our original graph probably looked like. Okay. Now here's the thing. That's not a surprise to us because if this is the derivative, we know that the original graph would have been x cubed. And that's what this is. This is a cubic function. Okay. Which is why I know that this should have come up higher, but whatever. But the thing is, there's no rule that says I have to be like centered here, right? I do want to make sure that since I have a slope of 0 here, this should really kind of flatten out more. Like I said, no one's judging your artwork here, but this should have probably come up a little higher like that. But I could have also drawn this same graph like here, right? Or I could have drawn it down here And that right there is the plus C effect, okay? That is the whole idea that when we do an antiderivative, we could have a constant added on to the end, and that constant is going to affect where on the graph this thing is located, okay, whether it slides up or slides down. So we'll get into that C a little more later on, but that's the idea, is that this would at least let me tell that like the shape of the graph does something like this. I can follow these slope lines like a little maze and figure out what my graph must have looked like. Okay. So the next one gets more complicated, and I think this is more what you would normally see with a slope field question. These ones are boring because we could do these by hand. We don't need a slope field to do them. But for this is saying that we're taking our x and y coordinates at each one of these spots and adding them together. So let's start in the middle here. 0, 0, that would be 0 plus 0 according to my differential equation. So that is going to have a slope of 0. But when I go here, this is 0, 1. So 0 plus 1, that's going to have a slope of 1. And 0 plus 2 is going to have a slope of 2. Okay, so this one's going to be a little different at every point. It's not going to all go in nice columns. There are still some patterns you can catch on to. But if I go over here, 1 comma 0 should have a slope of 1. So my goal is to make it look similar to this one. Okay. This would be 1, 1, which has a slope of 2. And then 1, 3 is going to have a, I'm sorry, this was 1, 1, so a slope of 2. So 1, 2 would have a slope of 3, which means I want that to look higher than my 2. Okay. So now would be a great time to pause the video and see if you can fill in the rest of this slope field on your own. I'll wait a second and then I will continue. What I did with this one is I said, okay, if 0, 0 makes a slope of 0, then 1, negative 1 would also make a slope of 0, right? 1 and negative 1. So I'm going to have a 0 slope here. I'm going to have a 0 slope at 2, negative 2. I'm going to have a 0 slope at negative 1, 1, and I'm going to have a 0 slope at negative 2, 2. So all of those are 0 slopes. Kind of along the same lines, like right here, this is negative 1 comma 2, so this would also be a 1. Remember, this was a 1, this was a 1. And I'm betting this would be, let's see, 2, negative 1. This is also a 1. So I do have sort of a diagonal pattern going on here. So for example, these should all be 2's, right? And I'm trying to make all 3 of these look the same. These are 3's, and this one is a 4, which I'm trying to make look higher than a 3, but it's hard when you make them too steep to begin with, you know? Okay, so this is negative 1, 0. So this slope should look like a negative 1, which means this is also a negative 1, and this is also a negative 1. And if you're not sure about that, add them together. This is 1 comma negative 2. So 1 plus negative 2 makes a negative 1. Okay. This is negative 2, 0. So this is going to make a negative 2. We want to be a little steeper than that. This is going to be a negative 2. This is going to be a negative 2. Trying to make all of those kind of in line. These ones are negative 3s, so trying to go steeper with that. And then this is going to give me a negative 4. So this slope field looks a little crazy, right? Depending on where I draw my function, this graph might look very different. So this function might, if it starts up here, do one of these where it kind of comes down like this and then swoops upward, okay? Or this function might start down here and kind of curve downward like this. We're not totally sure. That should match that tangent line a little better. And this is one of those cases, like, I don't know how to anti-differentiate this. I don't know how to find the antiderivative by hand. So a slope field is my best bet at figuring out like what might this original function have looked like. And it's kind of wild. These ones with the x's and y's, these things look like things that you have not seen before, okay? These, by the way, are like those implicit differentiation problems that we did at the beginning of the year that had the x's and y's in them, and the graphs look really strange. We are going to learn how to do some of these by hand. There's some techniques that we learn. This is one that even with those techniques, we would not be able to do an antiderivative. There are some differential equations that we just can't find a solution for. And so then a slope field is our best bet. Okay. So What I'm looking for when you draw one of these slope fields, when you sketch a graph in, like I said, I'm not going to judge your artwork, but I should see things like if you hit somewhere with a zero slope, we're obviously supposed to be changing direction, right? We're supposed to have that's a critical point. Okay, so we should see that in there somewhere. I also shouldn't see you blatantly like crossing over a slope field line. I mean, little mistakes like this should not be intersecting this line. It should be running more like alongside it. But um, so little things like that, I'm not going to get super nitpicky about. In general, I just want to see that you're kind of following the direction of those little tangent lines. Okay, so let's do something a little more mathematical. I do think we have one more example where we have to draw a slope field. This one's a little bit easier. So we're going to graph the slope field for the differential equation where it's dy dx equals 2x. Okay. This one, there's a lot of dots here, but it's going to go pretty quickly. So like, for example, because this one is just in terms of x, if x is 0, then all of my slopes are 0. These are all zeros. If x is 1, then my slopes are 2. So I'm going to draw all of these in as 2's. If x is 2, then my slope is 4. Try to make that look a little higher. And if x is 3, then all of my slopes are 6's. These should be even higher still. Okay. When x is -1, my slope is a -2. So it should look just like these, but tilted the other direction. When x is -2, I'm looking at -4. So again, trying to go a little bit higher this time. And then here at -3, I should be looking at -6. So these ones should be practically vertical. That might be being a little dramatic, but so that's what my slope field looks like. And I hope that you can look at that and visualize what this original graph must look like. And you probably don't have to use your imagination too hard because you know what the original graph should look like. If the derivative is 2x, think about what y is, okay? Um, but this one gives me another piece of information. It says sketch the curve within the slope field given the initial condition f of 1 is equal to 2. So this is what's called an initial condition, obviously. And the initial condition is like an anchor point from the original function. So remember, when we have that plus c in there, what we're saying is we don't know where our graph is situated, okay? But if I give you even just 1 point from that original graph, that's enough to kind of figure out where this thing is supposed to go. So this graph has to contain the point 1 comma 2, which is right here. Okay, it has to go through that point. So that's enough for me to say, well, maybe my graph looks like this. Something like that, something along those lines. Okay. We know it's a parabola. Again, I hope that that's what you were thinking earlier when I said you should know what this looks like. We know it's a parabola, and that checks out with the fact that this is 2x because my antiderivative would be x squared. Okay. But an initial condition just gives you a point that you have to make your graph go through. So now let's talk about some verbiage here. It says integrate the differential equation, which it won't always say that, and use the initial condition to find the particular solution. So first of all, I just want to make it very clear that when I'm talking about differential equations and I ask for the solution, what that means is take your derivative and find the original equation. Okay, so the solution is just the original equation. It's the f of x. Okay, well, let's think about this for a second. How do you get from a derivative back to the original equation? Well, you integrate, okay, or you do an antiderivative. And so anytime you see me asking you for a particular any type of solution, I'll talk about the particular in a second, but anytime I talk to you about a solution to a differential equation, I want your brain going to integration. I want your brain going to antiderivatives. That's what we're trying to do here. Okay? So let's integrate this thing. So if I have the integral of dy dx, I'm essentially taking, whoops, dx. I'm taking the derivative of both sides here. So I'm going to say this is now the integral of 2x. Well, the integral of dy dx is just y, right? Like this is saying what is the integral of a derivative, and that should just take you back to the original y equals. And then this is saying, well, give me an antiderivative of 2x. Well, the antiderivative is x squared. And then we would throw a plus c on there. Okay. This right here is referred to as a general solution. General is when you have the plus c in there. Okay. It's before you figure out what c is. But that's exactly what we're going to do next, is we're going to go figure out now what must that c value be. And then we'll check it with our graph and see how right we were. So the fact that I have this initial condition, if f of 1 equals 2, I can use that to solve for what c must be. So this is saying x is 1 and y is 2. So if I plug that in, I'm going to get 2 equals 1 squared plus c. Subtract the 1 from the other side, and we get that c is equal to 1. And that now allows me to say that my particular solution is y equals x squared, no longer plus c, but plus 1. Okay. This right here is what's called a particular solution. So particular solution, sometimes I've also seen it called specific solution. That is just your antiderivative, but with the c value in it, like you solved for what c was. Okay. So you find the general solution, which is a fancy way of saying take an antiderivative. You already know how to do that. Okay. And then you're going to use some point that they give you to solve for what c must be. Okay. So example 3, here's the same wording. Find a solution to the differential equation, and it's giving you f prime. So the solution is going to be, what is f, right, instead of f prime. And we're just going to do an antiderivative. So antiderivative of 2x is x squared. An antiderivative of 1 is 1x. And then we're going to say, all right, we know we have a plus c. That's my general, right? That's my general solution. Okay. I want a solution that satisfies this. That's an initial condition. So I want it to make sure it contains that point. So the way I'm going to do that is I'm going to plug zeros in for x's and 1 in for y. This one's going to be kind of lame. 0 squared plus 0 plus c. Well, hey, my zeros are just going to cross out of there, and what I really have is 1 equals c. So then my specific solution, or my particular solution, is this thing again, x squared plus x, but with a plus 1. And you should find that if you were to take the derivative of that, if you were to find f prime, you would get 2x plus 1. Now, those solutions are not unique, or I guess I should say the solution is unique. This answer is unique if I have f of 0 equals 1, but those derivatives are not unique. So I could have some other equation, x squared plus x plus 5, that would have this same derivative, okay? But when I have one specific initial condition, I should be able to find one specific antiderivative. Okay, here's another way that these differential equations show up sometime. And I want you to look at this, and I know this looks a little frightening. Okay, it says verify that this thing is a solution to this differential equation, which really is just saying, does it make it true? Well, you recognize this notation, right? This is y double prime, and this is y prime. And then this is just regular y, which we have here. This is y. So before I start one of these, every time I look at like what derivatives do I need? And I find those. So we're going to have to remember chain rule here. I'm going to write out, this is y equals e to the 3x. And then I'm going to find y prime. Well, chain rule says I need a 3. And then I'm multiplying by e to the 3x. And then y double prime is multiplied by 3 again. So I'm going to end up with 9e to the 3x. And now I'm just going to take these things and plug them into this equation here. So this says to do y double prime, so 9e to the 3x plus 2 times y prime, so 3e to the 3x, minus 15 times y, which is e to the 3x. And I'm looking to see, does this equal 0? Well, this is 6, right? I can make that a 6e to the 3x. And then I can add these together because they're like terms. So these two together give me 15 e to the 3x. And then, whoops, sorry guys. Um, I'm subtracting 15 e to the 3x. And lo and behold, that equals 0. That's it. I verified. Okay, so that's all that's asking you to do. So this lesson on its own, I don't think is super tricky. It's kind of laying the groundwork for some trickier stuff later on. But I think you should be able to handle everything that I'm throwing at you here. As always, if you have questions, please feel free to ask.